Welcome to this FMSP online revision session for the module MEI Differential Equations, otherwise known as the DE module. MEI is the only exam board that runs this A-level further maths module as a separate part. In other exam boards it is dealt with in FP2 and FP3 modules. This session will look at second order differential equations, and mainly we're going to do so by looking at one particular exam question. That'll take us about 20 minutes. But just so you know what you have to do if you are taking the MEI DE module, this is the breakdown of the second order differential equations specification. These are the things you have to be able to do. I'm not going to talk in detail about them. I'm just going to tell you what this video will particularly cover. And we will be solving a homogeneous second order differential equation using an AE and CF auxiliary equation and complementary function. We'll be doing that. Although it will be in the context of a non-homogeneous one. You'll see how they link together. We're not going to be looking in detail about the different types of solution, although we will have to be able to interpret these cases graphically, or at least in our particular case we'll have to deal with graphs, and we'll need to find a particular solution. We're actually going to be doing all this in the context of a non-homogeneous case. So the general second order linear differential equation is the non-homogeneous one. We're going to have to do it using the homogeneous case and adding a particular integral. And we're going to be finding a particular integral in a simple case. We're going to have to interpret the case graphically as well, so we're going to be doing that. We're not going to be looking at simple harmonic motion specifically, or damped oscillations, so these two are not going to be part of this video, but we are going to have to model things graphically, and that seems, as you can see, to get mentioned quite often in their specification. We're not going to be looking in this video at higher order equations. So I hope that clarifies what we're about to crack on with, and we'll do it mainly by looking at an exam question which is following on the next page. Now let's look at an exam question from the January 2010 MEI DE paper. This is question 1, and it should be immediately obvious that this is straight out of the second order bit of the DE syllabus. You can see straight away that we've got a second order equation to work with, and I can see that because of this being a second derivative. It's worthwhile getting used to your naming conventions. This is a second order differential equation. It is linear. Why is it linear? Because each of these terms are not squared. They are just the derivatives, or y itself, the function. There's no squaring or cubing or higher order things. They are linear terms of y and its derivatives. So it's second order linear. It has constant coefficients, and it is not necessary to learn how to deal with non-constant coefficients in the DE course, although if they do throw one at you in the exam, they'll give you hints about how to do it. But they're constant coefficients. There's a 9, a 6, and 1 here, so there's nothing crazy going on there. And it's also a non-homogeneous, and that's because the right-hand side is not 0. And you need to be aware of that, because we're going to have to solve a homogeneous case in order to solve the non-homogeneous case. But that's all part of this, and there are lots of marks available because it's non-homogeneous and second order. In fact, there are 9 marks for getting a general solution, and that's what we're going to do first. So let's proceed by looking at just question part I, which means I'm going to ignore the rest of the question for now. We'll come back and look at it. I'm going to ignore for now most of the description and the wordiness. It's actually straight out of a question which feels like from the M3 module from MEI, where you've got a spring bouncing around. And actually the M3 and the DE modules go together very nicely. If you're taking both of those, well done. We're going to focus on the sort of abstract solving the equation rather than the mechanics modeling bit, but it is modeling something bouncing on a spring. So the first thing we need to do with any second order differential equation is get the auxiliary equation. Which comes from, as I hope you'll remember, assuming the solution looks like something to do with y equals e to the power of something times t. And I'm going to call that something lambda. If you assume that's the case, you very quickly realize that the equation simplifies, and we're also going to solve the homogeneous version of this, which means we're ignoring the right-hand side for now, and it becomes clear later on why that's really useful. So we're going to assume the right-hand side is 0. And if you do that, you get very quickly an equation which, when you cancel out some non-zero terms, you get a lambda squared plus 6 lambda. These lambdas come out from when you differentiate the e to the lambda t here. And then you get a 9 left over equals 0. And solving this equation gives you the possible values for lambda, so that this thing up here would solve the homogeneous version of the second order equation. This is a nice and easy quadratic. It is in fact a perfect square. think you'll agree that means that lambda has to be minus 3. And it's worth realizing this is a repeated root, and it's worth writing it down so you don't forget that this is a special case we need to realize. So it's one of the 3 cases you could get when solving a quadratic. You could get complex roots, you could get real roots. In this case we have got a real root, but it is a repeated one, and that's the 3rd case. Although it depends which order you were taught it in as to which number it is. Anyway, it's one of the options, and it needs to be realized that your version of your solution you guessed at, which is at the top here, doesn't cover the 2-dimensional flavor of it that we need. So what you need to realize is that your complementary function, which is code name for the solution to the homogeneous case, will be something like this. It'll be actually some constant times the thing we guessed at, and we now know that lambda is minus 3. But it will also be some constant times the sort of next order up, so you're multiplying that by t as well. This is going to be our complementary function. It's quite often written as if it was just e to the minus 3t outside, and then you just get a plus bt inside. So these a's and b's are going to be part of our general solution. We'd only be able to find them when we get some extra information. And if you remember from the previous slide, that was going to come in part 2. So I'm okay to leave that as it is. But this is not the solution to the differential equation. This is the solution to the homogeneous case. And this is not the homogeneous case. We've got to deal with this right-hand side. But that's a good stopping point. We've got the complementary function, which is the solution to the homogeneous case. And I hope that isn't too unfamiliar. So we should move on to the next bit, which is dealing with the right-hand side. And for that we need to find a particular integral. So to solve the non-homogeneous case, we just need to realize that the homogeneous case, if you dump it into your thing over here, into the left-hand side, would get 0 on the right-hand side. That's the definition of the homogeneous case. So all we need to do is add on a function to our solution that would get what we need on the right-hand side, and then added to that 0 that we already know we would get, we would create what we need. And that's the flavor of finding a particular integral. Now this right-hand side looks like trig, and that's the big key with these particular integrals. You figure out what it looks like, and you try a solution that looks like it's going to be sort of able to derive what you need it to do. So realize this looks like trig. In this case, I'm going to try a solution. I quite often write the word try for this. Try a solution which has trig in it. So I'm going to use alpha and beta for my constants. Some multiple of cos plus some multiple of sine. And my job really is just to find out what values of alpha and beta would fit into this equation to give me what I want on the right-hand side. So to do that, I'm going to need to differentiate these things, and this becomes very familiar with a bit of practice. You get used to the way the signs change. That's my first derivative of y and y double dashed. I could use dot here since we're differentiating with respect to time, y double dot. But let's stick with this for now. This becomes back to the original with negative signs. And that always happens with our trig particular integral. You get used to this flavor very quickly. Now I should put these into the original equation. This time I'm using the full version, not just the homogeneous case, because I want it to fit the particular integral on the right-hand side there. So dumping this in quite carefully, I'm actually going to use a c for a cos term and an s for a sine term, just to save some time. This is a useful little time-saving trick. I've got one lot of y double dashed, so that's minus alpha c minus beta s. I've got 6 lots of the first derivative, so I'm going to add on 6 lots of minus alpha s plus beta c, plus 9 lots of the original trial solution, which is 9 lots of alpha c plus beta s. And I need that to equal a half sine t, which I've coded as s. It's worth realizing if this was a sine 2t instead of a 1t, then I would be changing my particular integral trial solution to have 2 t's in there to make that fit better. Okay, now it's just a bit of an algebraic mission, so I'm going to tidy everything up here. I'm going to collect all the cosine terms together. And I think I'm going to do it in one go. I'm going to write cos t here and collect all those terms. There's a minus alpha, there's a 6 beta, and there's a 9 alpha. So minus alpha plus 6 beta. And what else have we got? A 9 alpha. Now let's do the same with the sine terms. I'll tidy these up in a sec. But I've got a minus beta, a minus 6 alpha, and a plus 9 beta. And you quite often get these sort of alternating things. You get a flavor here which is repeated with different signs, and the letters the other way around. And on the right hand side I've got a half sine t still. I've gone back to my full workings because I don't have to write sine out so much now. Tidying these things up and comparing coefficients, I need the number of cosines on both sides to be 0. So tidying this up and combining the alphas together there, I've got 8 alpha plus 6 beta must equal 0 because I've got no coses on the right hand side, and on the sine coefficient I have 8 betas minus 6 alphas must equal a half because I need a half sine t on both sides. And these are my two simultaneous equations. I've got two equations, two unknowns, alpha and beta in there, which I should be able to solve. In this case, it's always nice to get the flavour, which you quite often get, of the similar coefficients turning up, quite often with a different sign in one of them, and the symbols the other way around. But it always makes it a pain to solve. I'm going to solve it by making the beta coefficients 24. So I'm going to multiply this one by 4. I'll get 32 alpha plus 24 beta, and that still equals 0. And this time I'm going to get 24 beta by multiplying this by 3. I'm going to get 18 alpha, and that's got to equal 3 over 2. Combining these two, I think by subtracting the left-hand one, taking the right-hand one away from the left-hand one, I get 32 alpha minus 18 alpha, which I believe is 50 alpha. And that better equal minus 3 over 2. And that very easily gives me alpha is minus 3 over 100. All I've got to do now is find beta. And I think putting it back into this one is pretty quick. And without too much trouble, I think you will find that beta is 4 over 100. Otherwise known as 2 over 50, but it's quite nice to have this able to be written easily as decimals, because this is minus 0.03, and this is, get the minus there, and this is 0.04. That means we are done, and our final solution, which I'm going to squeeze into the box up here, is a combination of the complementary function, which I already have, and the particular integral. So here it comes. I had the e to the minus 3t, a plus bt from before, and that would produce 0 if I put it into that left-hand side. And to create the right-hand side as I want it, I now know that I will need my trial solution with the appropriate numbers. So I'm going to have minus 3 over 100 cos t. Make sure you read very carefully which letters you used for which coefficients, plus 4 over 100 sine t. And that is your general solution, and you have just earned 9 marks. Okay, moving on to part 2, we've got the general solution, but we do need to take into account the initial conditions, and they've told us that in the next bit. They've told us the displacement and the velocity are 0. It's important that you know the displacement is just our y value, and the velocity is the rate of change of the y value, otherwise known as y dashed or y dot. I should probably be using y dot, but I used y dashed in the previous part of the question. Both of them mean the first derivative with respect to time in this question. So let's use the information they give us. We know that y has to equal 0 when t is 0, which is what they mean by initially. So if I write t equals 0, then I know that my solution must equal 0. And my solution is what we've got from the previous question. So putting 0 into there, I need to have this. E to the minus 3 lots of 0 is just 1, so I've got a plus b times 0. So there's a 0 here, and then over here, putting 0 into trig functions only gives me the cos term, so I get minus 3 over 100. And that very quickly gives me a, capital A, is 3/100ths. It doesn't help me find b, but for that I need to use my velocity condition, and to do that I need to differentiate my general solution. So let's get y dashed or y dot. This is the tricky bit. We're going to have to use the product rule here, so we've got two functions multiplied together here. Use the product rule, leave the first one alone, e to the minus 3t, differentiate the other one. That's just going to give me a b value. And then do it the other way around, differentiate the first one. I'm going to get minus 3 e to the minus 3t, and leave the other one alone, which is a plus bt. And then continuing on differentiating all this, I'm going to have to get plus 3 over 100 sine t, because cos differentiates to minus sine, and then minus 4 over 100, plus 4 over 100 cos t, because sine differentiates to cos. So that is y dot or y dashed. I'm putting 0 in there because the initial velocity is 0. I need to get 0 equals, this is just 1 times b, so there's a b, and luckily my b is going to come into this, otherwise I couldn't help really solve it. I also know that I'm going to get 3 times 1, and in the bracket I've got a, but I know a is 3/100ths. I'm going to get b times 0, which is nothing, and I'm going to get plus 4 over 100 from the cos term at the end here. So this is nice and tidy, it's not too bad at all. 0 equals b minus 9 over 100 plus 4 over 100, leading me to finish off pretty quickly. If I add those together, I get b equals 5/100ths. And I've got now the full solution, which I've got rid of a and b. If I take the hundredths out, I can write it down like this. y equals e to the minus 3t over 100. And in the brackets I've got a, but I've taken the 100 out, so that's 3, plus bt, which is 500, but the 100's gone, so I've got 5t. And the rest of it is exactly as it was before. So maybe I should have factorized 100 out the whole of this thing, but I think it's nice to see it all separated out. And there we have the particular solution for our differential equation with its initial condition. This is worth another 5 marks, which is nice because these 14 marks are relatively straightforward and predictable. You've got to do plenty of decent algebra, but it's very doable and it's quite satisfying to be able to pull out a solution from a complicated journey like that. So part 3 is almost always asked about in these sort of questions as a follow-up to part 2. And if you have a solution, you should be able to describe what happens to that solution, particularly for large or small values of t. In this case, they've asked for over time, what happens to this? And by looking at the bits in your solution, you should be able to see this term here has a negative power with t in it. So as t gets large, this thing will get very small, and it will completely dwarf whatever happens in here. This thing will trump it. So this thing is going to disappear as t gets large. These two terms, the oscillating terms, the trig terms, are not going to get any larger or smaller. They're just going to keep oscillating forever because that's what cos and sine do. So the first thing to realize is that the e to the minus 3 term and everything goes with it will head towards 0 as t heads off to infinity, and this is a useful mathematical notation for saying that. But the rest of the solution will stay as it is, so y will approximately just be whatever's left. 4 sine t minus 3 cos t. We've just rearranged the order there, and we've still got this divided by 100. This will be an oscillating thing, and if you're feeling on the ball, you'll realize this is these 3 and the 4. This is maybe from a C3 or C4 bit of work. You could write that as a single trigonometry term. It would have an amplitude of 5 because there's a 3, 4, 5 triangle buried in behind the seeds here. But the point is, you need to say this is oscillating. And if you wanted to get bonus marks, they're probably not going to give you an extra, but it's approximately amplitude of 0.05 or 500ths. That would be the amplitude of the oscillations. But it is oscillating, and the other term will have died away. And that's where you're going to get the 2 marks for. One for saying the e to the minus 3t term does away, and one for saying that this is oscillating. And the fact that the amplitude is roughly 0.05, what you really need to say to get the mark is that it's roughly constant, because the other term is not doing anything anymore. And it's oscillating with constant amplitude. Okay, let's keep going. So bearing that in mind, the next question they ask you to tackle is what happens approximately, and really pay attention to this word, when t is 20 pi. Now I've left on the screen the solution that we got, and also the attempt I had at differentiating it, although I've left the a's and b's in there. It's important that you recognise the approximate, and what you've just done is recognise that when t is large, you know what's going on. This is sufficiently large to figure it out. So these terms that we were realising disappeared will disappear roughly by the time t is 20 pi. And since they only want approximate values, you should be using this. Which means the only terms that are left are the ones here, the cos and the sine terms, and when t is a multiple of pi, the sine term will be 0. So all that's left when t is 20 pi, we've got y being the displacement, is approximately minus 3 over 100, or 0.03, which is from this cosine term here. Now we do need to get y dot as well, or y dashed. But since we were looking at this earlier, you can realise this term and this term will still have that e to the minus 3t, and t is largish, so they're going to disappear. But this time the cosine term has the coefficient of 4 to the hundredths, so y dot on the velocity is approximately 4 hundredths, or 0.04. And that, believe it or not, is worth 3 marks for just having the intuition to realise that your previous question makes this one very easy. And so to the last part of this question. 24 marks for this question, there's still 5 to go, but they're an easy 5 if you've kept your head through the whole of this. So what they're asking now is that the motion of the platform, this whole thing you're modelling, is stopped at t equals 20 pi, the thing you've just been worried about in part IV. So you just have some information from the previous part about what it starts off by doing at this point. And the differential equation modelling becomes this, and you'll notice this is exactly the same as it was before with a 0 right hand side, so this is now the homogeneous case. And we have solved this already. We did it right at the beginning of the question, and let's have a quick look at the solution. I think it's this page here. So you can see that we solved the homogeneous case. You do not need to repeat the work, although the number of times the examiners will get tired of seeing people go through this again, I'm sure is quite entertaining. Read the examiner's report if you ever want a nice insight into how examiners' minds work. But we've solved it already. However, this is a different setup, so if you wrote down the same solution with the same letters, you would not get the marks. What you need to realize is, since this is just a homogeneous case, the solution will look the same, which means it will have the e to the minus 3t, but we need to be aware that the constants may be different. In fact, they almost certainly will. So using a and b again would be a bad idea, but using the next letters might be just a good idea. So I think something like this would be the general solution. You don't know what c and d are. You probably could work them out approximately, since you've done the work in part 4, but all they want you to do is write down the general solution and sketch it. So this is where you need to use part 4. But here's a quick axis. And you need to realize that at 20 pi, you said that y was approximately, let's put the approximation signs there, minus 0.03, and that y dot was approximately 0.04. With that information, you need to sketch this thing. So let's say this is 0 here, somewhere along the line is 20 pi. And you need to realize that this thing must be true. So let's mark 0.03 below the axis. There's minus. It must start here. And you also know which way it's going to go. Looking at the solution, this is a solution which dies away because you've got this minus power. As t gets large, this thing heads towards 0. Now there's no oscillating terms left over at the end here, so this thing is not going to oscillate, it's just going to die off. But it's starting below the axis, so it must probably remain below the axis. And you also know its gradient. The velocity, remember, is the gradient of the thing, so its gradient is positive. It's going to be starting by heading off, so I think with that information you can quickly sketch something heading up like this. And anything which looks roughly like this is going to get the examiners excited enough to give you some marks. In fact, you're going to get 5 of them for this minimal amount of work. Again, they're testing your knowledge of what you've done and why it's useful, rather than just the sausage machine, turn the handle and get the answer. But this is an easy 5 marks if you keep your head screwed on and remember what you answered in part 4. And that is the end of our question. For the sake of clarity, I'm going to include the mark scheme for this question. So if you want to have a quick look at what the examiners would give marks for, you'll probably need to check the codes for all the sort of short acronyms they use in mark schemes, but getting used to them is very important for your revision. Here is page 1 of the mark scheme. If you want to pause the video and have a look, you can. And here is page 2 of the mark scheme for this question, and you can see that the way they break the marks down is quite carefully noted there. So thanks very much for listening. This has been an online revision video for the Further Maths Support Program for the Differential Equations module for MEI. And if you want to know any more about any other revision modules, check out the website at the bottom of the page there.